This is not some DVD floating in space. It's a megastructure that might one day become humanity's home. The Earth might not remain habitable forever. It could get engulfed by a massive solar flare, or become too hot due to climate change, or have all its life wiped out by one enormous asteroid. What if I told you we could outlive all these disasters? And that we could do that by building a space megastructure bigger than the sun itself. Just how big would we have to make it? And what would life be like on a structure like that? This is What If, and here's what would happen if we could build an Alderson disk. Why would we colonize other currently uninhabitable planets if we could hypothetically build a habitat of our own? Something that would host many billions of future humans without ever running out of space. It does look like a DVD, doesn't it? Only it has the mass of 3,000 suns. The reason why we'd need our Alderson disk to have such a huge mass is gravity. All objects with mass are gravitationally drawn to each other, and objects with a greater mass have a greater gravitational pull. For the Alderson disk to be stable enough to host life, we'd need it to have a stronger pull than the sun does. That's where it gets tricky, because the sun is the most massive object in our solar system, accounting for 99.8% of its total mass. To have enough material to outweigh the sun, we'd have to get it by breaking down every planet, moon, and asteroid in a radius of hundreds of light years around us. Or we could give our Alderson disk artificial gravity. This type of gravity isn't caused by attraction, but by acceleration or centrifugal force. In other words, we'd have to spin our disk fast enough that it doesn't collapse into a donut or get swallowed by the sun. But since we haven't really figured out artificial gravity yet, let's stick with the first option and make our Alderson disk very, very massive. 241 million kilometers wide. That would make it stretch past the orbit of Mars. It would also be several thousand kilometers, or miles, thick, and would have a surface area equivalent to over 1 billion Earths. Just imagine how many billions of humans could live on it. But not so fast. Our Alderson disk wouldn't be habitable everywhere. And before I explain that, let me talk about the sun for a moment. Our sun would be sitting stationary in the hole at the center of the disk. And because of this, our disk would have no day and night cycle, only a never-ending twilight. But since our disk would have a bigger mass and a stronger gravitational pull, there's a chance that the sun would wobble up and down. That would somewhat solve our day and night problem, but it could also increase the possibility of colliding with our star.
Before we get to the next episode, I just want to take a moment to tell you about an amazing product we've been working with called Opus Clip. You know, we run multiple YouTube channels here at Underknown, and with those big YouTube channels, well, shorts are a big part of what makes them great. They're amazing ways to connect with our fans and spread more educational content, but making the shorts can be pretty tough. Time-consuming. You know, that's where Opus Clip comes in. We've been using it here at Underknown to make viral shorts incredibly fast and effectively. It uses this really cool curation model to analyze and pick out the best parts of our video and then seamlessly rearrange them into shorts that can stand on their own. It's like taking our favorite parts of each video and cutting them into bite-sized pieces that you can all enjoy. And what's even better, if you're a creator trying to get into short-form content, well, Opus Clip is for you. You can try it free by going to opus.pro. Link in the description.
We might need to install gamma ray lasers to have more control over the sun's wobbling. And still, our disc-shaped world would need way more things to become suitable for us to live on it. One of the most important things is an atmosphere. On Earth, the atmosphere protects us from harmful ultraviolet radiation. It reduces temperature extremes, and it creates pressure that allows liquid water to exist. We'd need an atmosphere to do all the same things for our Alderson disk. And to keep the sun from stealing it, we'd need to build a wall around the disk's inner edge. Unlike Earth, the Alderson disk wouldn't have liquid metal in its core to give it a magnetosphere. A magnetic field is important because it keeps the solar wind from stripping off the atmosphere. Without it, the solar wind would erode the part of the Alderson disk closer to the sun. This could make the entire structure unstable and possibly destroy it altogether. Once we figure out how to make the atmosphere and magnetic field, we could bring in water. We'd make holes in the disk that would allow for oceans. Because of the way gravity would work on our Alderson disk, the water could be suspended. The oceans on the disc-shaped structure would literally be bottomless. For the same gravitational reasons, humans would be able to live on both the top and the bottom side of the disk. For those living on the bottom side, it wouldn't feel as if they were walking upside down. It would be just normal on each side. But of course, this space megastructure could have some flaws. Because of the disk's enormous mass, its gravity might make it collapse into a gigantic torus, or even worse, a black hole. Then there are asteroids. Even though we used up all the nearby asteroids to form our Alderson disk in the first place, there's no guarantee new interstellar space rocks wouldn't come and bombard our disk world. And not just asteroids, but rogue planets as well. Even the slightest hit could destabilize the disk and plunge it right into the sun. Speaking of the sun, remember I said that not all of the Alderson disk would be habitable? That's because the sun wouldn't be heating it evenly. The inner side of the disk would be very hot. To withstand the tremendous heat, we'd have to give our disk a heat shield, just like the one we developed for the Parker Solar Probe. The outer edges of the disk would be freezing cold, but the middle band of the structure would be just perfect for life. Although there would be a lot of unused space, the habitable area would still be 50 million times larger than the entire surface of Earth.
Rockets are incredibly powerful. You can launch yourself into orbit, fly the moon, and soon enough, travel to Mars. But to go beyond our solar system, you're going to need something else. Solar sails. How exactly would sails work out in space? How long would it take you to travel to the edge of the solar system? And why could this journey end with your slow and lonely demise? This is What If, and here's what would happen if you sailed the galaxy on solar winds. To launch a spaceship, you need a rocket to push you up into the sky. That push is called thrust. Being launched from Earth with the power of a rocket gives a spacecraft most of its momentum. After this, you need more fuel to change your speed or course. But there are no gas stations out there in space for you to refuel, and that means you can only go as far as your fuel takes you. You see, more fuel means more weight, and in space, your reserves are limited. In other words, it would be really hard to get to your interstellar destination with rockets alone. But all of that is about to change. All aboard! You're set to sail across the galaxy. On Earth, sails have been moving boats around the globe for centuries. They work without any fuel.
only the power of wind. But out in space, there are no air particles moving around, so you'd need to harness a different kind of wind. Solar winds carry charged particles ejected by the sun. These particles fly across the solar system at a blisteringly fast 1.6 million kilometers per hour. But with a special type of sail, you could take advantage of that power to get yourself across the solar system and beyond. And no, those special sails wouldn't look much like the sails you're familiar with. Are you ready to have your mind blown? This is the contraption that could take you across the galaxy. It's called electric sails, or e-sails. They're kind of like an umbrella without fabric, only these ribs would be made of electrically charged aluminum wires, and they can be as long as 20 kilometers, while also being no thicker than about half of one strand of hair upon your head. Now, all you'd need is the solar wind, and you could sail across the deep, dark sea of outer space. Wait. There's one catch. You see, you'd still need chemical rockets to launch you off into space to begin with. That's because electric sails don't work within Earth's magnetosphere. The magnetosphere is the area around the planet that's under the influence of its magnetic field. It's up to 10 times larger than Earth itself. And to escape it, you'd need a little boost from the old school rockets. Or you could build a spaceport around Earth. It would have to be far enough so that the planet's magnetic field doesn't reach it. But, that would get too expensive and take too long to construct, and we want to send you on this journey right now. So you'd launch your ship from Earth and out of the magnetosphere's limits. From there, it would be smooth sailing. With a 1,000 kilogram spacecraft like yours, you'd have about 100 wires to catch solar wind particles. You'd be a pioneer voyaging through space with this fantastic new technology. After 1 year of sailing, you'd reach a speed of at least 30 kilometers per second. And you might even go as fast as 150 kilometers per second. Yeah, and that's really fast. Faster than Voyager 1, the fastest space probe humans have ever sent off-world. The Voyager 1 probe is hurtling through space at about 17 kilometers per second. After spending 3 years getting past Mars, Jupiter, Saturn, and Uranus, you'd end up beyond the orbit of Neptune. You'd navigate by simply changing the voltage levels on different wires of your electric sails. Yeah, well, you'd still have to be a navigational genius to sail safely, especially when you get closer to the outer edges of the solar system. Here, you have to pass through the Kuiper Belt. This area is filled with icy comets, and if you're not careful, these comets will do some hefty damage to your electric sails. Yeah, your interstellar trip might end before you even get out of our planetary neighborhood. After that, you've still got a long way to go to the very end of the solar system, the heliopause. It's 4 times further away from the sun than Neptune. So fasten your seatbelts and power through a pretty uneventful view for about 10 more years. Yeah, I know, you'd prefer a view of Jupiter or Uranus instead. But hey, it's almost time to explore worlds you've never seen. Ooh, I just remembered I was supposed to tell you something important. Yeah, you know how your electric sails need solar winds to sail? Well, now you'd be the furthest from the sun you've ever been, and that means there won't be as many solar particles pushing your spaceship forward. Your sailing might just come to a complete stop, leaving you stuck forever in the outskirts of the solar system. Cold, lonely, and hopeless. yeah, I'm not gonna lie, this could be how your days come to an end. So, while you still have some life left in your sails, you'll need to navigate to another star. If I were you, I'd head to the Alpha Centauri star system. It's the closest one around, and it has not one, but 3 stars. Now, you should also know that not all stars are equal in providing you the powerful solar winds you so desperately need. Passing by a red dwarf star like Alpha Centauri C, also known as Proxima Centauri, you'd experience luminosities that could be anywhere from 1/10 to 1/10,000th as strong as our own sun. But despite this, you might be able to gain enough accelerating power to reach super high speeds once again. And all this without any chemical fuel. Yeah, going green is the cool new thing everyone's talking about. That's no moon. It's a space station. The enormous planet-killing kind, designed for only one thing: to bring order to the galaxy. It's Star Wars' Imperial superweapon, the Death Star. What would it take to build a star like this? Where would we assemble the universe's biggest weapon of mass destruction? And what unfortunate planet would be the first target for our test firing? This is What If, and here's what would happen if we could build the Death Star. I've got a bad feeling about this, but it took the Empire 19 years to build their first Death Star, so we'd better get started. It's unclear exactly how big the DS-1 orbital battle station was. Estimates vary between 120 kilometers and 160 kilometers in diameter. That's substantially smaller than, say, our moon, but compared to some of the smallest moons in the solar system, it's enormous. And we'd only need one thing to build it. Money. Lots of money. Big projects cost big money. In this case, we're talking $852 quadrillion. 852 with 15 zeros. And that's only the cost of construction. Once the Death Star is ready, keeping it up and running wouldn't be any cheaper. Weapon or not, this space station would require 1.7 million staff to run the station's retail shops and troop cafeterias. Add 25,984 stormtroopers and 342,953 Imperial Navy soldiers, and you'll get 2,068,937 people living aboard the Death Star. If each person on the Death Star created 1.13 kilograms of waste every day, it would cost $564,925 daily not to turn the Death Star into a landfill. That doesn't include people who fell into a trash compactor and weren't able to blast their way out.
Come in, 3PO!
The daily electricity bill would add up to $52 billion, $274,000 to feed the crew, with another $20,400 to supply tea or coffee, $233,000 for one cycle of laundry. You wouldn't expect your troopers to run around with dirty underwear, right? The total for keeping the Death Star operational would amount to $7.8 octillion every day. That's more money than we currently have here on Earth. And it doesn't include the cost of a single blast of super laser. That would be an additional $8 octillion. Still feel like firing lasers into planets? Okay, then let's talk about how you could build the Death Star. You already know it would come with the price tag of $852 quadrillion, but where would you start assembling this super weapon? First, you'd need a hypermatter reactor core. Let's not go into the specifics of how such a reactor would work, and we'll just assume that you already have one. You'd build 4 reactor shafts, all joined along the equator, and a large column running from top to bottom. This column would help to distribute power and also act as a station stabilizer. This mega project would require a lot of steel. By some calculations, the Earth has enough iron in its core to provide for 2 million Death Stars. But you wouldn't want to sacrifice our planet for an army of deadly weapons, would you? Even if you took only the amount of iron needed for one Death Star, it would take over 830,000 years to produce enough steel so you could begin construction. And it would take millions of rocket launches to get the steel where it needed to go. By the time the Death Star was finished, this might make our atmosphere so polluted that we'd be forced to move away from Earth to another planet. And where would we build the Death Star anyway? We can't get too far from our planet, but you definitely don't want that thing in Earth's low orbit. There's too much of a chance of it falling down to Earth. You could start building outside of the Earth's atmosphere. Just make sure to not accidentally blast our planet with the super laser. Speaking of the blast, well, in reality, light doesn't behave that way. Instead, it would keep moving in whatever direction it was fired.
Sorry about the mess.
By the way, destroying an Earth-sized planet would require a lot of power. You'd need to spend a week collecting all of the sun's energy before you could fire up the Death Star. And don't stand anywhere close to the beam at the moment of the blast. So much energy right next to you, even when not aimed directly at you, would cause you to evaporate in a matter of seconds. Then there's the recoil. The third law of motion teaches us that every action has an equal and opposite reaction. That means if you packed a big enough punch to destroy a planet using the sun's energy, it would send the Death Star in the opposite direction at a speed of 77 kilometers per second. That's unless you had an antimatter device aboard the Death Star. Antimatter is matter, but with its electrical charge reversed. When antimatter meets matter, the two destroy one another. That's why you'd need only 0.00000002% of a targeted planet's mass in antimatter to turn that planet into space debris. In this case, the recoil would be almost unnoticeable. But you'd better not aim that Death Star at any planets in the solar system. There's a better application for this weapon. It could be used to vaporize any asteroids that could be a risk for our planet. Although a giant death orb might be a little overqualified for the task. At least when an interstellar asteroid is hurtling in our direction, we'd be ready to knock it out before it destroys us.
I've got a bad feeling about it.
Quiet.
What?
The Earth may not be our home forever. Eventually, we may have to leave. What if, instead of finding a potentially habitable exoplanet light years away, we stayed in our solar system and built a habitat so enormous we could never overpopulate it? This is What If, and here's what would happen if we built a ring world in space. Imagine you lived on a ring with a radius of 150 million kilometers encircling the sun. A gigantic artificial world with its own gravity, ecosystem, and atmosphere, big enough for trillions of humans to call home. You'd live on an enormous landmass on the inner side of the ring. The outer shell would protect you and all those trillions of people from the hazards of outer space. How does that sound? Yeah, great. Problem is, assembling such a thing suspended out in the solar system wouldn't be easy. You couldn't just pull the Earth apart and have an army of robots reassemble it into a ring world. Among the many problems you'd run into, your first would be finding the material. The International Space Station, roaming the Earth's lower orbit right now, weighs about 420 tons. Something like a ring world would tip the scales at no less than 1 million tons. Where would we find all this material? I know some places. The Kuiper Belt beyond the orbit of Neptune would do just fine. This ring of icy bodies stretches out for almost 3 billion kilometers. Some astronomers think the Kuiper Belt would have enough material for this project, but it's hard to tell exactly how much we'd need to construct a thing like this. We might have to sacrifice all the planets, moons, and asteroids in the solar system. our ring world and the sun would be the only things left. If we could manage to gather and transport all the material available, then construction would begin. It would take a lot of physical labor, an army of robots, and maybe hundreds of generations to realize that our structure was not stable enough. Because the megastructure would turn out so enormous, it would break any known molecular bonds. We'd have to find a way to make use of one of the fundamental forces of nature, the strong nuclear force. Of all forces, it's the grippiest. It bonds material on the scale of atomic nucleus so that nothing can break it apart. Or maybe we'd come up with a new, super strong material altogether. But until we figure that out, every interstellar body passing through our solar system would be a threat to our megastructure. The next thing we'd have to worry about is gravity. And that part is pretty easy. We'd just have to spin the ring world at nearly 2 million kilometers per hour. I know, that's really fast. We'd have to build up that speed over time. Luckily, maintaining it in the frictionless environment of space wouldn't be too hard. Such rotation would generate centrifugal force, and that, in turn, would create an artificial gravity equal to the one we have here on Earth. With gravity solved, we'd bring in the atmosphere and start populating the ring world. For the inhabitants of the megastructure, it would always be daytime, unless we could create a day and night cycle with extra panels inside the ring. But for all the epicness of the world we just created, it wouldn't be stable. A single asteroid strike could cause the structure to drift closer to the sun. A hole punched through the ring could let all our atmosphere out. And a massive solar storm? Don't even get me started on that one. One failure inside the ring could doom the entire structure together with its inhabitants. It's just too risky to build it around the sun. We might have better luck with a huge ring space station in the Earth's orbit. What if we could engineer a gigantic megastructure capable of harvesting every bit of the sun's energy? Something known as a Dyson sphere. How long would it take to construct this mega shell? Where would we find all the materials needed? And what could we do with the structure once we finally built it? This is What If, and here's what would happen if we could build a Dyson sphere around the sun. The idea of a Dyson sphere was, well, stolen from aliens. In 1960, astrophysicist Freeman Dyson theorized another civilization that found a way to meet their ever-increasing energy and space demands. They rearranged their solar system. This hypothetical advanced civilization built a hollow sphere around their own sun and provided themselves with an incredible amount of energy and habitable real estate. But what about us? How would we go about building this space-level structure? Theoretically, if we built a Dyson sphere, we'd have access to a colossal 400 septillion watts of solar energy. That's 1 trillion times more power than our entire civilization consumes today. The problem is, no known material is strong enough to handle all the space radiation. And even if we created one in very large quantities, a tiny gravitational pull towards the sun would make our solid sphere uninhabitable. Not to mention that it would be totally unstable. Every meteor strike would push a part of the sphere towards the star. But all these issues can be solved with a simple adjustment. Instead of building a solid Dyson sphere, we could build a Dyson swarm, a myriad of solar collectors with their individual orbits around the sun. Let's start with a small station, one that's able to provide the energy needed for this whole construction project. We'd begin on Mercury. It would become our space mine for the iron and oxygen we'd need. From those elements, we'd make highly reflective solar collectors. The giant mirrors would reflect light into a small solar power plant. From there, it would beam the energy to where we need it. We'd probably demolish Mercury entirely before we moved on to Venus, Mars, and the outer planets. Even nearby asteroids would be decimated. However, even just deconstructing Mercury would supply us with enough energy to power up our supercomputers and boost interstellar exploration. Maybe we'd even build Earth-like oases, large rotating space colonies in the habitable zone of our solar system. Maybe if we're lucky, we'd find other, more efficient sources of energy to help us master space travel. One day, we want to take humanity into space, but why don't we start small? Take one solar power station, 10,000 people, and 10 million tons of crumbled moon rock, and you get A space habitat, a Stanford torus. How would this habitat work? Who would be allowed to live there? And how would it help to reverse climate change on Earth? This is What If, and here's what would happen if we built a Stanford torus. We've already hypothesized about living on an O'Neill cylinder, a Dyson sphere, even a Matrushka brain. How would this habitat be any different? For one, its size. A Stanford torus would be about 60 times smaller than an O'Neill cylinder. And it's much, much smaller than a Dyson sphere. To build a Stanford torus, we'd need to mine the moon a little. The moon is a perfect mining candidate because it has oxygen in its rocks that we could use to make a breathable atmosphere and manufacture water. It has silica we'd use for windows and solar cells. It also has aluminum that would work perfectly for construction. But of course, securing the materials is only the beginning. We'd start assembling the habitat in space, between the moon and the Earth. It would have to be close enough to the moon so that we could easily transport the materials. It would also need to be far enough from the Earth that it wouldn't fall into our planet's orbit. Our Stanford torus would look like a bicycle wheel, and the spokes would join together at the center. The inhabitants would live in the tire section. But before we bring people in, we need to create a proper environment and life support. To imitate the Earth's gravity, we'd make the habitat complete a full spin on its axis every minute. The centrifugal force would make up for the weightlessness you normally experience in space, because you don't want things to float around. The habitat would get all its sunlight beamed down by a large mirror stationed directly over the hub at a 45-degree angle. It would direct solar rays into the smaller mirrors on the outer shell of the torus. Those mirrors would also act as part of the shield from all the harmful cosmic radiation. Living in this space habitat would be like living in a small town. There would be no skyscrapers, only labs, high-tech farms, and housing. Most of the people living on the Stanford torus would be scientists or engineers, farmers or space construction workers. They'd take up a permanent residence on the torus with their families, where they would live a sustainable colony life. The population of the Stanford torus would be limited to about 10,000 people. All the inhabitants would be strictly selected through extensive tests and training. But we wouldn't just build the habitat for the sake of it. The Stanford torus would benefit deep space research and act as a maintenance and construction point for satellite solar power stations. The solar power stations would provide for all the colony's energy needs and would have the potential to supply energy to Earth as well. We'd beam solar energy down with lasers or microwave emitters. Then we would collect that energy above the Earth's atmosphere. Having so much solar-generated power, we wouldn't need to burn any fossil fuels. Give it enough time and our planet might just recover from climate change. But all that wouldn't be cheap. The cost of a Stanford torus would come to some $900 billion. But we could minimize a large chunk of that cost by using reusable SpaceX rockets to send people to space. Eventually, we'd start building more habitats and explore more of the solar system. We'd build a lunar base and then set a course for Mars. But before you sign up for that mission, you need to have a good survival strategy in case something goes wrong. And we have a show for you that covers just that, to help you survive whatever awaits you. Global warming continues to get worse. It's destroying our land and killing our people. But what if there was a way to stop it almost instantly? We might not even need to sacrifice our cars or change what we eat. Instead, we could build a shield to block out the sun. How would this help climate change? How possible is something like this? And could this end up being a bad thing for the Earth? This is What If, and here's what would happen if we built a sun shield in space. A sun shield would be like a massive umbrella in space. It would divert rays from the sun, reducing heat and solar radiation on Earth. It's been proposed for decades by scientists and could one day become a reality. But there's a couple of conditions. It would cost trillions of dollars, and every country on Earth would need to be on board. Easy, right? Well, let's just assume this happens, and we'll just skip to the good stuff. The sun shield would be created by sending small flyers up into space. They would have incredibly thin mirrors and would connect to make one massive umbrella. It would be half the size of the Earth and located 1.5 million kilometers away from the planet. At this location, it would be the same distance from the Earth all year round. The shield would block out just 2% of the sun's rays, which would reduce the Earth's temperature by about 1 degree. That was the Earth's temperature just before the Industrial Revolution. As more flyers are added, the sun shield would change Earth's temperature gradually. This is so we don't shock every living species on Earth with a sudden temperature change. As this happens, tropical climates will get colder and the Arctic will be able to stay frozen for the first time in decades. Decreasing the Earth's temperature will also affect the water cycle. We would have fewer heavy rainstorms, hurricanes, and flooding. But if we got rid of climate change, would humans continue to act as they do today? People and big industries might still release lots of carbon dioxide and methane. Since we'd have conquered global warming, humans might go ahead and create even more greenhouse gases, and then they'll all get trapped in our atmosphere. But at least we wouldn't have to worry about climate change, right? Well, not quite. It is possible that something could go wrong with the sun shield, like getting hit by an asteroid or drifting out of position. We'd have to adjust the shield every few years, and if we forgot to do that, the consequences would be devastating. If we didn't replace the shield at the end of its 50-year life cycle, we'd be hit by a global temperature change faster than ever before. Instead of the Earth's temperature increasing over years or decades, it would happen within a couple of months, by up to 3 degrees. This increase in temperature would be a huge shock to everything on Earth, including the planet itself. Certain areas would become more prone to droughts, while others would have massive floods. This would destroy our infrastructure and cities. Crops would also die, and water would be harder to obtain. Antarctica would be melting again, while drier areas would be burning with wildfires. And with this happening so quickly, species wouldn't be able to adapt, and that includes us. Millions of people could die, and hundreds of species could go extinct. And since people didn't decrease the amount of carbon dioxide and methane we released into our atmosphere when we had the sun shield, it would be too late at this point. The Earth would continue to heat up until our planet becomes an unlivable desert. So having a sun shield shouldn't be seen as a bandage for climate change. Instead, it should be looked at as a possible second chance for humanity to make up for its mistakes. But due to the astronomical cost, it's unlikely a sun shield would even be built. Do you ever question the nature of your reality? Are you real? Or are you a product of some complex computer simulation? What I'm about to tell you might change the way you perceive the world. And it all starts with a cosmic megastructure the size of our solar system. This is What If, and here's what would happen if we could build a Matrushka brain. We've talked about cosmic megastructures before, but this one isn't like any other. To understand what a Matrushka brain is and how it could change your outlook on life, we need to start from the beginning. A Dyson sphere. In 1960, a physicist and a seeker for alien life, Freeman Dyson, came up with the idea that advanced extraterrestrial civilizations would build space megastructures around their host star. They'd do it to collect all of their star's energy and fuel their travels across the universe. Or they'd simply use the structure as real estate. Location, location, location. Then, almost 50 years later, an inventor by the name of Robert Bradbury gave new meaning to Dyson spheres. According to his calculations, by the year 2250, humanity would become advanced enough to start building a megastructure similar to the one proposed by Dyson. But instead of having just one sphere around the sun, we'd stack them around one another, just like the Russian Matrushka dolls. What materials would we need to build a structure like that? How far into the solar system would our construction stretch? And most importantly, what would we be using this Matrushka brain for? We'd start with a single Dyson sphere. We'd use this first shell to draw the energy from the sun. A Dyson sphere would give us so much solar energy that it'd be enough to power the most advanced computer in the universe. I told you, a Matrushka brain isn't just any megastructure we could live on. It's a giant supercomputer, the size of the solar system. The shells of the Matrushka brain would expand from the orbit of Mercury beyond the orbit of Neptune. They'd be passing energy from the sun down to the last outer shell. We'd have robots mine Venus for its rocky silicate mantle until there's nothing left of it. But silicon isn't the only thing we'd need for this construction. The shells of the Matrushka brain would be made of a material called computronium. It's a hypothetical material we've yet to invent, but the idea behind it is that every particle would be a tiny computer capable of passing computer codes to other particles. The Matrushka brain would start writing its own code, building itself and expanding far into the solar system. It would be capable of calculating and predicting every event from human interactions to cosmic occurrences. Its processing power would have no limits at all. What would it mean for us to have unlimited computing power? How would we use it? Building a megastructure like this would make us a Type 2 civilization on the Kardashev scale. It's a scale that characterizes civilizations by their energy disposal level. A Type 1 civilization is one that's tamed all of its planet's resources and can control the weather, earthquakes, even volcanoes. A Type 2 civilization can harvest all the energy of its host star. With all the energy of the sun at our disposal, we could become intergalactic travelers. Yeah, we could leave our solar system and go explore what's out there. We could relocate to other planets if we wanted, but most likely that's not where we'd end up. With the computational power of the Matrushka brain, we could simulate an alternate digital reality. We could leave our physical bodies behind and upload our brains into that virtual world. We'd become a new species, immortal entities with unlimited computing abilities. We'd create our own universes with our own rules. Or maybe we'd recreate our world and control every aspect of it. Well, that said, how can you tell if you aren't already inside a Matrushka brain? Right? Doesn't this make you question your entire reality?
Before we get to the next episode, let's take another moment to tell you about how we've been making our short-form content here at What If. For the past while, we've been using this awesome service called Opus Clip. Let me show you how it works. All you have to do is upload or link your own long-form video, and then Opus Clip magically takes the best parts of your video and creates a standalone short from it. What's even cooler? Well, each video has its own viral rating. This is where the AI predicts how well your video can perform. Opus has a bunch of new features as well, from being able to upload to social directly from the site to manually reframing your clips. So if you're a creator who wants to get into short-form content, Opus Clip is for you. And the best part, it's totally free to try. Go to opus.pro to check it out. Link in the description.
Tired of living on an overpopulated Earth? Why not move to the O'Neill Cylinder, an artificial state-of-the-art space habitat where we can control everything, including the weather. What would it take to build a space station like this? How big would it be? And how would we make it suitable for life? This is What If, and here's what would happen if we could build an O'Neill cylinder. When physicist Gerald K. O'Neill came up with the idea of his space colony in 1974, people thought he was crazy. Back then, a cylinder floating in space didn't seem like a space habitat anyone would want to move to. But fast forward to our time, the world has grown by 4 billion people. Climate change is on the rise. Moving to a space station doesn't seem so crazy anymore, huh? Now, this far-fetched idea inspires wealthy dreamers like Jeff Bezos, who is looking into building enough O'Neill cylinders to board 1 trillion people. But how exactly would this work? The idea behind the O'Neill Cylinder space station is simple. It would be a rotating space station about 6.5 kilometers in diameter and 26 kilometers in length. To build a structure that size, we wouldn't need to collapse all the planets in the solar system like we would for some of the other space megastructures. Mining our moon and some nearby asteroids should be enough to provide us with all the materials we'd need. We'd assemble the cylindrical station right in space, somewhere between the Earth and the Moon. We'd park the O'Neill cylinder at a Lagrange point where it would stay in place without being drawn into the orbit of either the Earth or the Moon. Constructing the O'Neill cylinder would be one thing, but we'd also need to make it habitable. That means giving it gravity, water, and a breathable atmosphere. Gravity would be easy. The cylinder would make a full rotation in 2 minutes. That would generate a centripetal force, which we would experience as gravity. To make the structure more stable and prevent it from drifting away, we'd need to build 2 counter-rotating cylinders connected at each end. We'd design the space habitat to mimic Earth's air pressure at sea level, and the built-in aluminum mirrors would give us control over the amount of sunlight getting inside the habitat. We'd be able to set our own day and night cycle and manage the temperature inside the O'Neill cylinder too. This space habitat would be powered by solar energy, gathered by all the solar panels covering the outer cylinder. We'd create artificial mountains, valleys, and forests. We'd bring in water derived from icy comets. To get around the cylinder, we'd use cable cars, or you could simply ride a bike. It would be like a mini Earth, but with us having complete control over its climate. All that would take 6 years and a few $1 trillion to build. And if you don't want to give up your home on Earth for some space habitat, the O'Neill cylinder would make a great vacation spot. Welcome to O'Neill Cylinder 1, where there's no gloomy weather and where all your food is grown at a local farm. Climb up our artificial mountain and enjoy a great view from our space habitat for the low price. Of course, there would be some challenges. We'd have to get really good at recycling all the waste aboard the space habitat, or it would quickly turn into a space garbage bin. Then there are the asteroids. We'd have to keep track of how much damage they cause when they hit the O'Neill cylinder so that the situation doesn't get out of hand. And if something went wrong on the O'Neill cylinder, we could always use our Plan B. Mars might be a harsh place to move to, but we've got some tips for you on how to survive the Red Planet. Check out our new show that will help you survive whatever awaits you. What if someday we decided that the usefulness of our planet had run its course, and humans needed to scour space to find somewhere new to live? But instead of finding a potentially habitable Earth-like exoplanet light years away, we'd build our own artificial world right here in the solar system. What kind of technology would we need to manufacture a new planet? Where would we find enough raw materials for our future world? And how long would it take us to finish this planetary construction project? This is What If, and here's what would happen if we built an artificial planet. Rocky planets like Earth are born from the leftover material of a newly formed star. They start off as grains of dust smaller than the width of a human hair. These grains fuse into larger chunks that keep colliding with each other until, after a few million years, they develop into a new terrestrial world. Theoretically, we understand how planets are formed in the universe, but how would we go about manufacturing an artificial one? If we humans were to build a planetary replica and populate it, we'd have to churn out a rock with an atmosphere of breathable air, the right temperature, Earth-like gravity, and a stable orbit around the Sun. And that's just for starters. We'd start the construction in the Sun's habitable zone. That would help us maintain Earth-like temperatures on our artificial planet. But where would we find all the materials to build it? Asteroids might seem like a good source. The problem is, the Earth has the mass of over 2,000 asteroid belts. There's simply not enough asteroids in the solar system to build a new Earth-sized world. But there could be enough materials in the Oort cloud, the swarm of icy debris that, hypothetically, exists in the outermost reaches of the solar system. But this cloud is so far away that even Voyager 1, that's been traveling at 17 kilometers per second for the past 41 years, won't reach it for another 300 years. And it won't make it to the other side of the Oort cloud for about 30,000 years. We'd need to build some faster spacecraft to get all that dust and nudge it in the right direction. We could also start stealing moons from other planets. All of Jupiter's moons, for example, would give us enough material to craft a planet about 7% the size of Earth. That would be a good start, if we could manage to pull them out of Jupiter's orbit. It wouldn't be necessary to build our new world as big as the Earth to replicate the same force of gravity we feel now. If we could pack 1/10 of the Earth's mass into a sphere the size of the Moon, it would do the same trick. Still, it would take us at least several hundred years to finish the construction. Once all the engineering issues were solved and our newly formed artificial planet settled into orbit around the Sun, we'd dump in some water. We'd let it evaporate to create the atmosphere. We could even inject some of the carbon dioxide released by polluting industries on Earth. Then we'd bring in the plants. Plants would slowly build up oxygen in the atmosphere through photosynthesis. Finally, after millennia of planet building, the first human colonies would set foot on the new terrestrial human-made planet. Even though it would be smaller in size, the Earth's replica wouldn't seem much different from the original. Earth-like temperatures and gravity would make it feel like our home planet. But it wouldn't be as stable as the Earth. Our artificial world would require active maintenance, from the planetary environment to our orbital parameters. Currently, there's so much we don't know about the universe, and we can only guess how a new planet would form within it. At this point, it may be easier to terraform an existing world instead of building a totally new one. Are you ready for the trip of a lifetime? Because this not-so-little machine is about to take you on one. A trip back in time. What would you need for this time travel to happen? How would it mess with your body? And what do black holes have to do with all this? This is What If, and here's what would happen if you built a Tipler time machine. Theoretically, building a time-traveling device is possible, or almost possible, All you'd need to do is to assemble an enormous cylinder and get yourself a spaceship. Then you'd need to figure out how to make the cylinder spin at a few billion rotations per minute. And remember when I said it was enormous? Well, for this cylinder to work, its length would need to be infinite. Before I get into the explanation of how this time machine works, let me give you a bit of a backstory. In 1915, Albert Einstein came up with his theory of general relativity. He claimed that our universe can be described by 4 dimensions. The first 3 would be the dimensions of space, and the 4th would be time. Together, they're space-time. Gravity can bend space-time like a bowling ball would bend a rubber sheet. The bending of space-time makes time slow down. The passage of time also changes depending on how fast you move. The theory of general relativity blew people's minds, but in 1974, Frank Tipler realized that solutions to equations of general relativity could be used to build a time-traveling device. Now that you're all caught up, let's start building this machine already. First, you'd need to find material with the total mass of about 10 suns. Where you'd find all that matter is a big question, of course, but let's assume you managed to strip all the neighboring star systems and assemble them into a cylinder somewhere above the Earth. 10 solar masses worth of matter is no joke. It would take up a lot of space, and you would have to figure out how to compress all that matter. It would have to be so dense that it would turn into an elongated black hole. There's no time to worry about getting sucked into it. Now that you've finally assembled a Tipler cylinder, you'd need to make it rotate at an unimaginably fast rate, a few billion times every minute. Theoretically, instead of condensing a whole lot of matter into a black hole and then having to deal with the cylinder rotation, you could just find a few neutron stars. Those are leftovers from gigantic stars that didn't have enough mass to collapse into black holes. And they rotate pretty fast. You could line a few of them up and synchronize their rotation. But even if you chose the fastest ones, their rotation wouldn't come close to a few billion times per minute. Besides, we did an earlier video about trying to bring a spoonful of neutron star back to Earth, and it didn't go that well. Anyway, regardless of how you achieve this effect, the massive gravitational pull of the cylinder, combined with the fast rotation, would create a frame-dragging effect. In other words, the cylinder would drag space-time along with it. That means that you could hop on a spacecraft and follow the spiral course of the cylinder. And that would take you back in time. Time would fold upon itself, and you'd find yourself in a closed, time-like curve. It's a loop in which your traveling into the past has always been a part of that past, so you wouldn't create any time paradoxes. If you change the direction of your travel, you'd go back to the future, or rather, back to the time you started your journey from. The Tipler cylinder's specialty is travel into the past, not the future. But hey, you could hang out with your favorite people from the past. Go see a real-life Jurassic World. You could even go back to the time when the Earth didn't have any life at all. But of course, there is a drawback. All that would only be possible if the Tipler cylinder had an infinite length. It would have to go on forever. But that's just impossible. You can't build something that has no end at all. If you tried to make a finite cylinder, then you'd have to deal with some exotic matter and its negative energy. But we haven't discovered it yet, and it doesn't look like we'll be getting our hands on this kind of matter anytime soon. I haven't even mentioned the effects of the black hole on your body. You'd instantly get sucked into the cylinder's black hole if you got close enough. But hopefully, there are other ways that would allow you to travel through time. And when you do, we'll be there for you and help you survive this kind of trip on our new show, How to Survive. This is not some DVD floating in space. It's a megastructure that might one day become humanity's home. The Earth might not remain habitable